Hello and welcome back. Let's continue to look at this question, which we are finding the equation for the tangent line for this function. So the tangent line is the one that will pass right by this function. It'll pass. It'll touch exactly one. It'll touch one point and pass by with the exact same slope. And we want to find the tangent lines at two locations: at x is equal to 1, at x is equal to -2. So in order for us to work with the slope of this line, we have to find the derivative. We have to find the instantaneous rate of change. So we did a bunch of work. We found the difference quotient, f of x plus h minus f of x over h. We simplified it down to get this guy here, and we took the limit as h goes to 0. So h, we were finding the slope. 2 points, the point slope from x to x plus a hair, so just a hair over, and we want that hair to shrink down to nothing, so that we're not going over pretty much at all. So when I take the limit of a rational function, again a polynomial divided by a polynomial, I can just plug in h into here. If h here is 0, I get minus 2x on top. If h here is 0, I get x squared times x squared on bottom, which is x to the fourth. My x's cancel out, and that gives us our derivative. So I need a little bit of space, so I'm going to start back up here from the top again. I apologize for having to erase my previous work. So now I want to find the equation of a line, and I know the slope of the line, or I can find the slope of the line. So let's do this at 1 first. So at x is equal to 1, this is one of the points that we want to find. Our slope is going to be -2 divided by 1 cubed, which is going to be -2. And this is our slope. And now I need to find a point that this passes through. Well, I know x is equal to 1, and I can figure out the y value as well. So x should be equal to 1. Where's our y equal? Well, our original equation for our function was 1 over x squared. So it's going to be 1 over y squared, which is 1. So I can use point slope form now to say that y minus 1 is going to be equal to -2 times x minus 1. So again, this is y minus the y value is equal to our slope times x minus 1. And I can turn this into, so this is point slope form, which absolutely works. But we could also turn this into y-intercept form if I solve for y here. So if I do some algebra, this is going to be y is equal to -2x plus 3, I believe. 2 times -2 times 1 at 1. So here's the same equation, just rearranged a little bit. And let's do the other point. So again, we have our equation for the slope of the line, and we want to find the slope at -2. So if I plug in -2 into here, I will get -2 divided by -2 cubed. -2 cubed is -8, so -2 divided by -8 should be 1/4. So our line is going to be going up because the slope is going to be positive. X should be equal to -2. So what is y? Well, y up here is going to be 1 over x squared. So 1 over -2 squared. This is also 1/4. Nice. So the equation of the line will be y minus 1/4 is equal to 1/4 times x minus -2. So it's going to be plus 2. And then this is in point slope form. A lot of people like it in y equals mx plus b. So if I solve for y here, I'll get y is equal to 1/4. 1/4 times 2 is a half, plus another fourth is going to be 3/4. So let's draw these and see if this makes sense. So down here, I have f of x is equal to 1 over x squared. So at the point x is equal to 1, we said that our slope should be -2. And it does look like that. If I were better at drawing, this would be a lot nicer of a this would be a lot better drawing. But essentially what we see here is that the slope is going to be -2, and our y-intercept should be at +3. And this matches our equation for the tangent line at exactly that point. If we draw the other line, so at y is equal to at x is equal to -2, our line looks something a little bit more like this. And again here, our y-intercept should be a little bit less than 1, which we have 3/4. Again, we have a positive slope for this guy and a negative slope for this guy. We had our negative slope and our positive slope. Everything looks exactly fine. What you'll notice here, though, is that our function doesn't exist at 0. I can't plug 0 into my function, but I also can't plug 0 into my derivative. So the derivative doesn't exist at 0. And this is not the only way that a derivative might not exist. Take a look at this line over here. We've got x minus 2, the absolute value of x minus 2 minus 1. And if I were to try to if I were to look at the slope at various points, okay, so the slope over here, yeah, I can find the slope, that makes sense. Over here, I can find the slope, that makes sense. I can find these tangent lines. But what line is tangent right here? Well, I only want it to hit at exactly one place, but I need the slope to be the same. Well, what is the slope there? Is it flat? Is it kind of coming down like that guy? Is it coming down like that guy? It turns out that this line does not have a derivative right at this point here. And so we can talk about where a function is going to be differentiable, meaning where the derivative exists. And there's a few things that will need to happen. So again, a derivative is just a limit. So we need that this limit exists. So the limit has to exist, and for a limit to exist, the limit from both the left and the right direction have to be the same. So I have that as number 2 here, but first and foremost, this limit has to exist. However, to find the limit at a point, you have to plug in f of x, which means f of x also has to exist at that point. So this is something that's kind of hidden in the details a little bit. So in order for a function to be differentiable, f of x has to exist. And sort of as an extension of that, we even need that f of x has to be continuous. So let's look at an example of a function and see where our function is going to be differentiable. So here we've got a few points. I'll label the important points here. So out here at x1, we're not differentiable. I'll abbreviate this. differentiable. And why? Well, as we look at the slope coming down from the left-hand side, our slope is negative, right? We're coming down the line. But our slope from the right-hand side is exactly equal to 0. It looks like it's just a flat line. So we have different slopes coming in. So the reason here is because we have what's called a corner. Where the slope coming in from both directions is going to be different. So the limit doesn't exist. The limit from the left and the right are not going to be the same. We have different slopes on either sides. At x2 right here, our function is not going to be differentiable because it's not continuous. Continuous, I abbreviate as CTS. And again, this if it's not continuous, we can't find the derivative there. If we want to look for the slope, well, how do I draw my tangent line? I have to draw it so that it intersects this line, but it has to be at the same slope as here. It doesn't really make sense to try to draw this tangent line in here. Everywhere else in between, you've got a nice smooth line. You know, no kinks, no corners. Everything's fine. We have another discontinuity at the third point here. So again, it's just not continuous. At x4 here, we have another corner. So this is not going to be continuous there. But also at x5, it's not continuous again. So these are essentially two common ways for a derivative not to exist. We either have a corner where we have different slopes coming in from the left and right hand side, so that our limit here isn't going to exist. If we take the limit approaching from the left or the limit approaching from the right, we will get different slopes coming into the point. If it's not continuous, this throws things off as well. But there is one final situation over here. What we'll notice is that this line starts going straight up. And I could draw a tangent line right here. And this tangent line is going to be going straight up. So the question is, what is the slope of a vertical line? And the answer is, it has no slope. And this is one of the situations that we have to be careful of. If you have a horizontal line, this slope is 0. A vertical line, this slope is undefined. So at x6 over here, we have no slope. So no derivative. Oops, that's not how you spell derivative. In the next and final video, I'll do another example of something that has no derivative at a point. But here are three common ways for a function to not have a derivative, to not be differentiable at a point, either from corners, not being continuous, or having a vertical section.